Hello everyone, welcome back to Active Learning. Our discussion in this video will be about the sinc function and a sequence of integrals involving this function. The sinc function of x is defined as the ratio of sin x to that of x. For the purposes of our discussion, we will be using a scaled form of the function that is more prominent in signal processing applications. The sinc function in the context of Fourier transforms becomes an immensely useful tool, and its transform plays a key role in smoothing out signals with sharp spikes. We'll exploit this connection, and with some help from the Fourier inversion formulae and the convolution theorem, we'll be able to evaluate a series of integrals involving the sinc function with a beautiful visual approach. Consider a simple function f of x with a sharp spike. One way to blur this spike is to define a new function h1 of x such that h1 of x is the average of f of x minus 1 by 2 and f of x plus 1 by 2. We divide the unit interval centered at x into two equally spaced points and define the new function's value as the average of these 2 points. The function so created will have fewer sharp points because of the averaging process. Naturally, we can extend this process with more points. Just modify the definition of the new function and we will get a finer version. As the number of divisions approach infinity, the sum in the definition approaches an integral of the function between x minus 1 by 2 and x plus 1 by 2. In other words, the new function at each x represents the area under the curve in the unit interval centered at x. We can manipulate the resulting expression by introducing the rectangle function that takes on a value of 1 in the unit interval minus 1 by 2 to 1 by 2 and 0 otherwise. Though we will focus more on the rectangle function in this video, the equation can be generalized by replacing it with an arbitrary function g. The equation here then defines the convolution between functions f and g, where the g of x function acts like a scaling function in the convolution process. Seeing that the rectangular function play a key role in our video, let's try and figure out the Fourier transform of this function. Because the function is 0 everywhere except on a unit interval, the limits of the integral become finite. Evaluating the resulting expression is elementary. With the help of Euler's formulae, we find that the Fourier transform of the rectangular function is the sinc function scaled by a factor of pi. Now here comes the cool part. The formulas for the Fourier and the inverse of Fourier transform are nearly identical, except for the negative sign in the exponent. With a simple change of variables, it is easy to see that for functions that are symmetric with respect to the y-axis, the Fourier transform of a Fourier transform recovers the original function. Therefore, we can immediately see that the Fourier transform of the scaled sinc function gives back the rectangular function. Specifically, at c equal to 0, we find that the integral of the sinc function over the real line is the value of the rectangular function at 0, which is clearly 1. To make this idea even more amazing, we make use of the convolution theorem, which states that the Fourier transform of a product of two functions is just the convolution of the Fourier transforms of the respective functions. And the converse is also true. Fourier transform has the effect of interchanging standard multiplication into a convolution operation. Let's put this into use to find the integral of the squared sinc function. From the convolution theorem, we know that the Fourier transform of the squared sinc function is a rectangle function convolved with itself. It's simple to find that the area of the intersecting region increases linearly, reaching a value of 1 at z equal to 0 and reduces linearly back to 0 again. Evaluating the integral at z equal to 0, we find that the integral of the squared sinc function over the real line is the value of the rectangle function at 0, which is again 1. We can do the same process again to find the interval of the sinc function, this time cubed. Based on the convolution, it should be easy to see that the resulting curve is a parabola on either side. In case it isn't clear what the value of the function is at z equal to 0, we only need to realize that it is the common area between the triangle function and the rectangle function. From simple geometry, it is easy to see that the resulting area is 3 by 4. We will do this one more time for integrating the fourth power of the sinc function. If we try to directly convolve the Fourier transform of the sinc function q with the rectangle function, we run into a problem. The resulting curve is a piecewise cubic function, and it isn't immediately obvious what the value of the function is at z equal to 0. Even finding the area of the convolution at 0 is unclear. Rather, the trick here is to treat it as the product of two sinc squared functions. The transform then becomes a convolution between two triangle functions. We need the area of the resulting convolution only at z equal to 0. If we treat one of the triangle functions as the scaling function in the process, the other triangular function gets scaled by itself at each point. That is, the function gets squared at all points, resulting in two parabolic arcs. As we know that the area of a parabolic segment is 1/3 of the surrounding rectangle, it is immediately obvious that the total area, and hence the value of the rectangle at z equal to 0, is 2/3. This idea can be used to evaluate more integrals. For example, here are two integrals which can be reduced to simple area calculations by means of the convolution process. Perhaps the most amazing use of this idea is in explaining a curious pattern in a sequence of integrals involving the sinc functions. This sequence of integrals evaluates to 1 up to a certain point, and strangely afterwards, it attains a value less than 1. We know that the Fourier transform of the sinc function is the rectangular function. Scaling the function further, the rectangular function gets squished along the x-axis and stretched along the y-axis by the same amount, still maintaining an area of 1 square unit. The Fourier transform of the product of sinc of pi t and sinc of pi t by 3 can be obtained by convolving two corresponding rectangle functions. Convolution, being a smoothing process, reduces the length of the topmost edge by 1/3. We know that the value of the integral with these sinc functions is the value of the resulting curve at z equal to 0, which for now evaluates to 1. As long as the length of this top edge remains greater than 0, the result of the convolution will be 1. As more sinc functions come into the transform, the subsequent curves get smoothened at every iteration, and the top edge gets shortened with every convolution. Though the top edge looks perfectly flat, a bulk of it is made up of piecewise polynomial functions, and only a fragment of the original segment remains. By the time sinc of pi t by 15 gets added to the transform, the length of the top edge will be 1 minus 1/3 minus 1/5 and so on up to minus 1/13, which is approximately 0.045. As sinc pi t by 15 gets added, the top edge is to reduce by another 1/15, approximately 0.067. Therefore, the edge disappears completely and the curve takes on a value less than 1 at z equal to 0 for the first time. Because the values at 0 represent the corresponding integrals, we have a visual proof explaining why the pattern breaks down after this point. Fourier transforms and convolutions have a wide variety of applications, ranging from signal processing to probability theory to polynomial multiplication to quantum mechanics. But that doesn't mean they can be fun. Hope you enjoyed the discussion. See you in the next video.